Okay, so this is where the old review ended and the new review starts. So we're going to start with, first of all, write the K expression for the following. KW. KW is just equal to H3O plus times OH minus. Now remember, I told you sometimes I would write H3O plus as H plus. So if you see, it's also equal to H plus OH minus. But they're using a lot more of the H3O plus, so I wanted to make sure that you were aware of that. All right, next one, Ka for the product for the acid HA. Remember, HA will dissociate in water, become H plus AQ plus A minus AQ. Anytime you have a plus or minus, it's AQ. This would also be AQ to start with because most acids are aqueous, but we do have some that are solids. All right, so to write the Ka for this, we do products over reactants to their coefficients. All the coefficients here are 1. So we just go H plus AQ concentration times the A minus AQ concentration divided by HA AQ. And we're done. All right, the next one is solve for the OH minus concentration and tell if the solution is acid, base, or neutral. Sorry, tell if. So here, remember that we had the block where we had pH goes to back and forth to POH, goes down to or up to concentration of hydroxide here on this side, goes over and back to concentration of H3O plus, and up and down to that. So you can go up and over. That is the safest way, but I found most kids make a mistake if they don't. So to do up and over, we would just take and go pH is equal to minus the log of that, and we plug it in our calculator. Negative log 6.5 times 10 to the negative 9, close parentheses, enter. And we end up with 8.187. I'm just going to carry that through right now. To get across the top, we would take 14 minus that. So 14 minus the answer would give me 5.81. At this point, I probably would drop the other one, but you could take it to 9 if you want to. Then to get down to the concentration of hydrogen, we go so 10 to the minus 5.8129 equals 10 minus 5.82129. And we get 1.53 times 10, actually 10 to 4, times 10 to the negative 6 molar. That's an answer. Now you can also, and you can do this, it's simpler, it takes less time, but you have to be careful. We can find the concentration of hydroxide by taking Kw divided by H3O plus. So Kw is 10 to the minus 14, and we would divide it by, in parentheses, 6.5 times 10 to the minus 9, close parentheses. And we will get the same thing. So let me put it through for you. 10 to the negative 14, enter, divided by, and this is where you have to have the parentheses. If you don't have the parentheses, you're going to get the wrong answer. 6.5 times 10 to the minus 9, and then you're going to close parentheses. Now, having said that, when you hit that enter, if you end up with something that has an exponent greater than 14, you know you did something wrong. Okay? If you didn't, then you probably did it okay. And you'll notice it's the same answer, 1.454 times 10 to the minus 6 molar. So you can do it this way. I just highly caution the parentheses. Okay? I'm going to do it that way here on this next one, just because it's a lot simpler and I'm running out of room. So again, the concentration of hydroxide is equal to W divided by the concentration H3O plus. So 10 to the minus 14 divided by 3.5 times 10 to the minus 3 in parentheses. So 10 to the negative 14 divided by parentheses, whoops, see I already did some mess up there, negative 14, enter, then divide parentheses 3.5 times 10, exponent negative 3, come down, close parentheses, enter, and I get 2.86 times 10 to the negative 12 molar. And that would be my answer. Okay? Now, I'm just going to show you really quickly the wrong way. So if I had forgotten 10 to the negative 14, I remembered to hit enter, did divide, and then I went 3.5 times 10 to the negative third, look at the difference in the answer. So we had negative 12, but now we've got negative 18 because it took the answer and divided it by 3.5, but then it took that answer and times it by 10 to the negative third. So just be really careful with that. Okay, going on to the next page. All right, what are the strong acids and the strong bases? You should know this. Remember the swoop on the right-hand side of the periodic table is HNO3 nitric acid. Then go down to H2SO4 sulfuric acid. Then go over to HClO4 perchloric acid. Then you start with your binary acids, HCl, HBr, and HI, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Oops, going too fast. The strong bases are on the left-hand side of the periodic table. They start with lithium, and you get lithium hydroxide, and it is in a Tetris pattern. Sodium hydroxide and potassium hydroxide, all in the first column. Then you slide over a column to the second column, and you start with calcium, and so it's the second column, it needs 2 hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Now, oftentimes, and I think there's a question in your homework, it takes magnesium hydroxide as being strong, and sometimes they say the first 2 columns, any hydroxide is strong. So take that with a grain of salt, but these are the strongest. And remember, strong means 100% ionized, 100% ions. Okay, so here we're doing find out what's missing. Remember that we've got our pH chart that we can use. Sorry, I ran to go get one real quick for you. Remember this lovely chart right here if you don't have one on you. This helps you to know where to go. So I've been given pH on this first one, which is right here. I've got to get to all the other 4 corners. Now I purposely did it this way. She is going to give you something and ask for one of these 3, the other 3. Okay? I want you to practice on all of them. So to get from pH to here, we are going to go 10 to the minus pH. So we're going to go 10 to the negative 3.5. And for here we'll get 3.16 times 10 to the negative 4. Now it's easier to go across here by taking 14 minus 3.5, 10.5, and then going 10, going down, 10 to the negative 10.5, and we get 3.16 times 10 to the negative 11. Make sure that you put times 10 to the negative 11, not e. All right, next one down. This time we're given this corner right here. Remember, it says H plus, but it really is also H3O plus. And I'm going to scoot out a little bit so you can see a little bit better. Okay. Bring that up a little bit. So we've been giving the H3O plus. So I can take minus the log of 1.5 times 10 to the negative 8. Come down, close parentheses, and that gives me the pH, so I get 7.82. Now I cannot use that again, which is nice. I can go across the top here, take 14 minus 7.82, 6.18, 10 to the negative 6.18, and I get 6.61 times 10 to the negative 7. So coming down again, now I start with POH on this corner. So I can go 10 to the negative 10.5, and I get 3.16 times 10 to the negative 11. I can take 14 minus 10.5, and I've got the pH, which is 3.5, and we've already done the 3.5 up here, so 3.16 times 10 to the negative 4, which these two were the same, so I could have caught that there too. Okay, coming down another one. This time you're given OH concentration, which is here on the bottom. We're going to go up, so we're going to take minus the log, negative log of 8.6 times 10 to the negative 5, and we get 4.07, 14, minus 4.07, we get 9.93, 10 to the negative 9.93, 1.17 times 10 to the negative 10. Okay, next one. So we're starting pH right here. We got to go all the way 4 corners. So 10 to the negative 8.9, that's an easy one to do first. 2.6 times 10 to the negative 9. 14 minus 8.9, 5.10. Always do 2 after the decimal if you can. No, they didn't here and here, but usually you take 2 after the decimal. 10 to the negative 5.1, and you don't have to put the 0 there, but 7.94 times 10 to the negative 6. And these should all have molarity, and I've been slacking and not putting them, but it is a concentration, so we need to tell what concentration it is. Okay, so next part. I'm sorry about that. What is the net ionic equation for acid base of the following? So you need to be able to write the formulas. So hydrochloric HCl with potassium hydroxide KOH. Well, that's going to be a strong acid, strong base. We're going to get salt and water. The salt is the inside, KCl, plus 1 minus 1, and the outside, HOH, makes water. Now it said, what is the net ionic equation? So this has caught a lot of people on the homework, so be careful. It says net ionic equation. This is the regular equation. It's balanced, but it's not the net ionic. Net ionic says, okay, HCl is going to split to HCl plus Cl minus, and it's AQ, but this marker does not write that small very well, so I'm not going to write it. K plus and OH minus, and this splits into K plus and Cl minus, and this is all of our solubility rules. So this is a chlorine, group 17, this is a potassium, group 1, this is group 1 and group 17, so they're soluble. This water is a liquid. It doesn't split. It comes straight down as H2O. Now, what we know is that some things are going to cancel, and those things are going to be the same on both sides. So remember, our arrow is right here. So if it's the same on both sides, like this chlorine and this chlorine, they're called spectator ions. So this chlorine and this chlorine cancel out as spectator ions. this potassium and this potassium cancel out as spectator ions. So what's left? Well, H plus AQ plus OH minus AQ yields H2O as a liquid. That's the net ionic equation. So this is what they're looking for. Okay. Now if we look at the next one, nitric acid HNO3 with, which means plus, calcium hydroxide CaOH2 gives me, outsides make water, H2O, insides make the salt, Ca, which has a +2, with NO3, which has a -1, so I'm going to need two of them. Now again, I need to balance it, so I'm going to need 2 of these and 2 of these. Now, to do the net ionic equation, again, 2H plus, 2NO3 minus, Ca, 2 plus, OH minus, I have 2 of them, arrow. This comes straight down to H2O, and this is going to split Ca plus 2 and 2NO3 minus. So again, looking side to side, what cancels out, I'm going to use a different marker because the pink just smeared. Ca plus 2 and Ca plus 2 are spectator ions. The 2NO3 and the 2NO3 are spectator ions. So what's left? Well, we end up with 2H plus AQ plus 2OH minus AQ goes to 2H2O liquid. Well, what we know is the 2's will cancel, so basically my net ionic equation is the same as above, being H plus OH minus yields H2O as a liquid. And that's my answer. Okay, which of the following salts forms a basic solution? It wants to know what a basic solution is, and that would be greater than 7. Circle in blue. So in blue, it doesn't want to work. Try this one. Circle in blue. There we go. So that's going to be something that is giving me a strong base and a weak acid. Okay, so we'll go through that in a minute. Okay, and which ones are going to be acidic, which means less than 7? Circle in red. We have a red pencil here, and those are equal to 7. Leave with a 0 circle. With a 0 circle? I don't know. We're going to use an orange circle. How's that? Or maybe a green. We'll use a green. Alright, so we've got blue, green, and red. So what we need to do with each of these is look at what will they make. I'm going to use a pencil, so hopefully it'll project, but we'll see. We split it up. The first one we add OH to, so this becomes NaOH. Well, that's one of our strong bases, so I put Sb. Then we take the second part and we put a hydrogen with it. This is actually H. This one's an organic, so the H goes at the end, which is weird, I know, but it does. But that's not one of our strong acids, so we say weak acid. Even if we put it at the front, we know it's not one of our 6 that we talked about earlier. So overall, this one is going to have a pH greater than 7. So that one we're going to circle in blue for base. Okay, I'm actually going to zoom in a little bit on this so we can talk about each one individually and you can see what I'm doing. Not a lot of room. So this one will split, we'll get LiOH and we'll get HNO2. Well, this is a strong base. NO2, that's starting to tricky here. NO3 is a strong acid, but NO2 is a weak acid. So again, we're going to end up with a pH greater than 7. So again, we're going to circle this one in blue. And again, I'm going to enlarge it even more because it seems to be a little bit hard to see. Okay, so this one I'm going to go up for a minute because I'm running out of room down here. So RB is going to go with OH, and I is going to be with hydrogen. So this is a strong acid, and RB is more of a weak base. So here we're going to have a pH less than 7, which is an acid, so we're going to circle this one in red. Okay, hopefully we'll have a little bit more room on the next one. So if you can see, as I'm adding OH to this side and H plus to this side, this is a weak base, and H2SO4 would be a strong acid. So here we're going to get a pH less than 7. I'm sort of shortcutting. I'm hoping you're following it. So again, this will be an acidic salt. Going to the next one. Na is going to go NaOH, and this is going to go H3PO4. That is not one of our strong acids, H3PO4, so it's a weak acid. NaOH is a strong base. So here we're going to end up with a pH greater than 7, which is a base. So I'm going to pull this out, do this. Now the next one, if we add Na with OH and H with Cl, we've got a strong base and a strong acid. When we have a strong base and a strong acid, the pH equals 7. That is neutral. So NaCl gets our green neutral. We go to lithium with a hydroxide is a strong base. HNO3 is a strong acid. Again, pH is going to equal 7. So we're going to highlight this in, oops, let me slide over, sorry. I'm going to highlight this one in green. All right, next one. KOH is a strong base. HCl is a strong acid. Again, pH is going to be 7. Strong base and strong acid give us 7. Okay, NaOH or NH4OH is a weak base. It's not one of our strong ones. HBr, though, is a strong acid. So our pH here is going to be less than 7, which is red. And then the last one here, whoops, grabbed the wrong pen. NaOH is a strong base. H2SO4 is a strong acid. Putting them together, we're going to have again pH equals 7. So we're going to have another neutral. All right, hopefully that made sense. And there was more on the first one from last year that did with that. So if you want to go back and look at that, you can too. Next up, zoom back out again so we can read the whole thing. All right, how many milliliters, so we're looking for milliliters, of this are needed to neutralize this much of this? So it's a 1-to-1, so I can go ahead and use C1V1 equals C2V2, or here MA1V1 equals M2V2. Plugging in, we'll call this one V1, this one M1, this one V2, and this one M2. So I'm looking for V1. Rearranging, V1 is equal to M2V2 divided by M1. Plugging in. 1.243 molar times 14.2 milliliters divided by 0.324 molar. Molars will cancel. Plugging into our calculator, 1.243 times 14.2 divided by 0.324. Oh, something's way wrong. Let's try that again. I didn't clear first. Times 14.2 divided by 0.324. Much better. So volume here is 54 point, and then I had 3 significant figures, so I'm going to take 54.5 milliliters. And I'm done. Okay, next one up. Again, how many milliliters? So V1 equals question mark. We've got M1 here. We've got V2 here, and we've got M2 here. Check. 1 hydroxide, 1 H, so I can go right to the equation. I don't have to use a balanced equation. So again, we're going to use V1 equals M2V2 divided by M1. Plugging in 34.2 milliliters times 2.243 molar divided by 5.324 molar. Molars cancel. 34.2 times 2.243 enter divided by 5.324. 14.4 milliliters. Okay, next one up. Which of the following solutions containing an equal number of moles of each substance is a buffer? So again, buffers, we're looking for something that's not a strong acid and not a strong base. So first thing we do is cancel out anything that's a strong acid or a strong base, or the product of such. So those wouldn't work, this wouldn't work. And then we can look at what's left and say, okay, well, we've got this and this could go together and be a buffer. Now, some of you will be tempted to put these two together, but there's 2 hydrogens difference. Because there's 2 hydrogens difference, we can't use these because they're 2 hydrogens different. If they had put HCO3 minus, then yes, you could. There's nothing that goes with NO2, so it can't be used. So there's just one buffer that's a possibility here. Okay, for the next part, what is the molarity that's needed to titrate? They give you an equation. Here's a hint. It's a 2-to-1 ratio. So we do have to know something about that. Easiest possible thing is to take what you have given and change it to moles, and then do the 2-to-1, and then go forward because you'll make less mistakes. So we know molarity is equal to moles divided by liters, right? So we've got molarity, we've got milliliters. So in order to find moles, we're just going to take molarity times liters. So plugging in molarity, 0.324 molar times by 34.1 milliliters. But we got to change that into liters by dividing by 1,000 milliliters in 1 liter. And we get 0.324 times 34.1 divided by 1,000. 0.1010 moles. And that's out of the CaOH2. Well, looking at the equation, for every 1 of the CaOH2, we need 2 of the HCl. So just a real quick thing there will let us have moles, so times 2. 0.0220, I would just do a 1 there. You can see why. Okay, 1, and that is moles of HCl. And now remember, moles divided by liters is molarity. So to find out the solution here, concentration, we're going to take and divide that by our 25.5 milliliters, but we got to change it to liters, so 1,000 milliliters in 1 liter. Liters will go out. So let's times it by the 1,000, and then divide it by 25.5, and we got 0.867 molar of HCl. Done. All right, next step. We've been given the Ka. We've got the concentration of the acid and the base, and it wants to know what the pH is. So here we're going to use Henderson-Hasselbalch, where the pH is equal to the pKa plus the log of the concentration of the acid. Let's see, Can't remember if it's acid or base. Double check that equation before we get going. Real quick check is not a bad thing to do. It's the base over the acid. So the base over the acid. So this is my acid because it has the hydrogen. This is my base because it has a salt on top of it. So plugging in, we go minus the log of 1.8 times 10 to the negative 9 plus the log so to get pKa, we're minus the log of it. Minus the log of this is equal to pKa. So just so that you know. Log of my base 0.245 divided by 0.23. So let's do each of those steps real quick. So clear, minus log 1.8 times 10 to the negative 9, come down, close parentheses, we get 8.74, and then clear. We take the log of the concentration, 0.245 divided by 0.23, close, and we get 0.027, and we add that to 8.74, and we get 8.77 as the final pH. So it would be basic. Okay, which of the following diagrams properly depicts the dissolved species of NaOH? You had a lot of these in your homework problems. NaOH is a strong acid, or strong base, sorry, strong base. Because it's a strong base, it will totally dissociate. So we should have no NaOHs together. So because there's NaOHs together here, that's not a possibility. Same here. Now it's between these two. When NaOH dissociates, we get Na plus and OH minus, and that's it. This one has H pluses in it, so we cannot have that. So final answer is that one. Okay, coming over to the other side. Feels like we're going forever. Okay, when phosphoric acid, actually I'm going to pause this or stop this, and I'll put a second video up with the last 2 pages because I need a drink. It's a lot of talking.